overview. Yeah. Overview of my series of talks. In fact, it's about 4 talks, I think, maybe just exactly 4 talks. And the overview are, as you see, the first part, just homogeneous Riemannian manifold and their description. We will recall some very basic, very important properties and the methods of studying of homogeneous Riemannian spaces, manifolds, and some very, very important formulas, some very important results will be considered. It's just today. The next talk, it's some special classes of Riemannian homogeneous spaces. I want to discuss some very important and popular classes, look like symmetric, weakly symmetric, normal homogeneous, naturally reductive homogeneous spaces, and some other, for example, Gerobata spaces and Woloch spaces, generalized Woloch spaces. Why this? Because these classes are quite natural in different problems. They naturally appears when we're studying some well-known problems. And another reason is that if we have some conjecture, for example, for Riemannian geometry, then these special classes give us some examples which we can use to check our conjecture in some special cases. It's very easy, not very, but relatively easy, because we have some special simplification in the case of Riemannian homogeneous spaces, and so on. Okay, then the third talk will be devoted to quite important class, geodesic orbit Riemannian spaces. This could be defined as manifolds. All geodesic are homogeneous, or in other words, every geodesic of such manifold is the orbit of one-dimensional group of motion. It's very natural geometric description, very natural geometric definition, but in any case, it's not so easy, but we will see that some very, very good, very well-known spaces are subspaces of this, are subclasses of this class, and therefore it's very reasonable to study this class as a special object. And finally, my first talk will devote it to some problem related to Ricci curvature on homogeneous Riemannian spaces. Ricci curvature is quite serious, quite important characteristic of curvature of Riemannian manifold, and there are many interesting and open, in fact, problem related to this notion. Hence, I think it will be interesting for somebody or for some participants of this course, of this seminars, to see some results, to study some very recent approach, and so on and so on. I hope it will be interesting. Hence, our lecture starts with some notations and so on. In what follows, we deal with smooth C-infinity smooth manifolds. Of course, any remaining structure is also supposed C-infinity smooth. Why? Because any homogeneous Riemannian space has natural analytical structure. Therefore, we have no restriction seriously. More detailed description of various objects discussed below could be found in our recent book which was written jointly with Professor Berestowski from Sobolev Institute of Mathematics. This book, Remaining Manifolds and Homogeneous Geodesics, contains many interesting information, almost all information from this course, and a little, not a little, but much more information, of course, because we try to collect all interesting results on homogeneous Riemannian manifolds in this book, not only result, but methods, approach, and so on and so on and so on. Okay. Now, a little more about notation. Our notation are quite usual. For example, Riemannian manifold, we will denote usually as a pair, some manifold, and some metric tensor. In this case, mg. Then for any point of M, this symbol mx denotes the tangent space to M at the point x, more or less usual notation. This symbol nabla means the covariant derivative for the Levi-Civita connection on a given Riemannian manifold. Next, if X is a vector field on Riemannian manifold, then Lx means the Lie derivative with respect to this vector field. For the curvature tensor of Riemannian manifold, we adopt the following assumption as in book of Kobayashi and Nomizu. Yes. Yes, and a little about Lie groups and Lie algebra. For Lie group G capital, we usually denote its Lie algebra by this symbol or by symbol Gothic G. If this is a Lie bracket on G, then operator adjoint of Y. It is a linear operator on G such that it acts on X by these brackets, Y brackets X, as usual. For Lie algebra G, BG or simply B means Killing form of this algebra, which defined by standard formula, trace of composition at X and at Y. This should be capital X, of course. Next. Okay. Let's recall what is a Killing vector field. By definition, there are several equivalent definitions. The simplest way to define it is this equality. The Lie derivative with respect to X of metric is 0. It's equivalent to this one formula or to this another one formula. It's easy to check that these three formula are equivalent. This means that we consider any vector fields U and V on M. Yes, but X in this case is Killing vector field. Then sometimes it's useful to use operator AX, which is defined by these formulas, minus nabla V of X And if you check this formula, it's easy to check that this operator is Q-symmetric. It's more or less standard things. In fact, we will use it not so often. And in any case, I will recall what we need to use. Okay. Another very important property, all Killing fields on a given Riemannian manifold constitute a Lie algebra with respect to natural operation of vector fields. It's also very, very important. Now, the isometry group of any Riemannian manifolds is a Lie group. A Riemannian manifold is called homogeneous if its full isometry group acts transitively. This is equivalent to the fact that the Lie algebra G of all Killing vector fields is transitive of Riemannian manifolds. Or it could be reformulated in the following way. G generates a tangent space to M at every point X. It's well known that isometry is Lie group and G Gothic is Lie algebra of isometry group of Riemannian manifold. Okay, there are very standard, very good books, and now we will see some reference. Note that the connected isometry group, isom O0, is also transitive of homogeneous Riemannian manifold if M is assumed to be connected. Moreover, some smaller connected Lie groups could act on M transitively by isometries. It's very interesting discussion, and we will see something a little later. Now, okay, let's consider any Lie group G acted not necessarily transitive on Riemannian manifolds MG by isometries.
Yuri, just
Yes?
one question from Boris. He is asking, do you assume that G is compact? M is compact?
Not necessarily.
Okay.
Because like your definition of homogeneous, in one case it's homogeneous and the other is like almost homogeneous or locally homogeneous, right? When you switch from Lie group to Lie algebras, it's not equivalent, right?
Why not equivalent? It's the same.
Strip, right? Strip. So if you take strip, then it's locally homogeneous but not homogeneous.
Oh, yes, of course. Locally homogeneous, yes. If we consider, yes, for non-compact manifold, it's quite possible. Locally homogeneous, not necessarily homogeneous. Thank you. Yes, you're right. Okay, okay. The action of A on X, we denote by A of X. We identify the Lie algebra G of G capital with corresponding Lie algebra of Killing vector field as follows. For any element of Lie algebra, we consider one parameter groups by exponential, exponent of TU of isometries, and define a Killing vector field U tilde by usual formula. This is a yes, derivatives at the point T is 0. It's clear that the map is linear and injective, but we have this this connection. The bracket between vector fields on the manifold is the minus vector fields which corresponded to bracket between original vector fields in Lie algebra. The reason is that the Killing vector field are right invariant, but we consider as a Lie algebra the left invariant vector field on Lie group. The most important case for us is when G is transitive isometry on MG. The above identification allows us to apply the Lie theory to study particular properties of Killing vector fields. Okay, Now a little more about notation. Let G be a transitive isometry group of Riemannian manifold and consider any point X on the manifold. Then H of X, its isotropic group. Is this group contained all elements A such that they don't move the point X. They, by other word, it is a subgroup which fix the point X. This group called isotropic group or the stabilizer at the point X of M. It should be noted that the isotropic group at another point, say Y, is conjugate to this group HX in the group G. Indeed, if we have some element A such that A of X is Y, then isotropic group at the point Y could be calculated by this formula: A, H of X, A to the point -1. Therefore, up to conjugation, the isometry group is one and the same. Let's fix X and M and isotropic group H. Then the manifold M could be naturally identified with homogeneous space G mod H. We can consider the map phi from M to G mod H acted by this formula. Phi of Y is AH, where A is from G, H is the isotropic group at the point X. Okay, this map phi is correctly defined, bijective, and it is a diffeomorphism with respect to natural smooth structure. Since the metric tensor G is G invariant, we may consider MG as a homogeneous space G mod H supplied with invariant Riemannian matrix G. The Lie group G should not be connected, but the group G0, its connected component of the unit E, is also transitive on the space G mod H. Moreover, for some homogeneous space G mod H, there are some subgroups with the Lie algebra smaller than G acting transitively. Details could be found in the very well-known books of Bayanischik, for example. Okay, by the Hobbes-Hamilton theorem, every compact homogeneous manifold G mod H has non-negative Euler characteristics. Therefore, we have serious restriction, say, for some very well-known surfaces, two-dimensional surfaces, they could not be homogeneous because they have, say, negative Euler characteristic. Yes. Recall some properties of homogeneous manifold with positive Euler characteristics. A homogeneous space G mod H of a compact connected Lie group G has positive Euler characteristics if and only if the stabilizer H has the maximal rank. This means the rank of H is equal to the rank of G. Okay, and assume that the group G acts almost effectively. Then is semi-simple as universal covering M tilde is a compact homogeneous manifold of connected compact semi-simple group G tilde, which is a local isomorphic to G and is a direct product of simple Lie group GY. Its situation is only for case when Euler characteristic is greater than 0, positive Euler characteristics. Moreover, the homogeneous manifold is a direct product, G1 mod G mod H1 and so on, GK mod HK, where HY is defined naturally. Then every invariant matrix G small on M defined as invariant matrix on M tilde, and homogeneous Riemannian manifold is a direct product of homogeneous Riemannian manifold. Any of this homogeneous manifold has simple compact Lie group isometry G, Y. Okay.
So, Yuri, does it mean that we actually can study only the manifolds where the simple compact Lie group?
Yes,
And
yes,
then
really.
and
But only in the case when we have positive Euler characteristic. It's very special case, unfortunately. Yes, you're right.
okay.
This very important, very well-known propositional theorem by Constant. Yes, I recall it. A compact, almost effective homogeneous Riemannian manifold M G mod HG of positive Euler characteristic is irreducible as a Riemannian manifold if and only if the group G is simple. In particular, in simple and non-simple compact Lie groups cannot both act transitively and effectively as groups of isometries on a compact Riemannian manifolds with positive Euler characteristic. It's very, very serious simplification to study homogeneous manifolds, but it's a very special case, unfortunately, I recall it. Okay, let M G mod A is G mod H be a homogeneous space of positive Euler characteristic with a compact connected simple group G. The center of G is finite. Hence, it belongs to maximal torus T in H. So, if G acts effectively, it has trivial center. A description of homogeneous spaces of positive Euler characteristic reduces to descriptions of connected subgroups H of maximal rank of G, or equivalently subalgebras of maximal rank of simple compact Lie algebra G small. This very standard thing, classification of such subalgebra. Okay. An important subclass of compact homogeneous manifold of positive Euler characteristic consists of flag manifolds. They are described as adjoint orbits of a compact connected semi-simple Lie group G. We fix a point X in M, it considers some adjoint orbits. In other words, we have M is G mod H, where H is centralizer of non-trivial torus T in group G. Yes. In particular, the orbit of regular element of G is called full flag manifolds and is identified with G mod T, where T is maximal torus of G. Classical result on transitive isometry group of Riemannian manifolds with positive Euler characteristic could be found in various books, for example, on this one. Note also that every compact naturally reductive homogeneous Riemannian manifold of positive Euler characteristic is necessarily normal homogeneous with respect to some transitive semi-simple isometry group. We will discuss it a little later, and I recall this later. Okay. Now, what is a reductive space and why it's important? Okay. Let G small be a Lie algebra of the group G and H small be Lie algebra of isotropy subgroup H. A homogeneous space G mod H is called a reductive if there is a subspace, a reductive complement, P in G, such that G is a direct sum of H and P as linear spaces, and action of a joint operator of A on P is in P for any element A from the isometry group. It's easy to check for some concrete examples, but reasonable questions arises. Is it possible always to find reductive complement for any homogeneous space? It's not true. It's not true, but in fact, it's true for remaining homogeneous space. Not that at H of P is subset of P implies that bracket of Lie algebra H and P is in P. It's very simple corollary. Moreover, for a connected group H, this property are equivalent. If H is connected, it's the same, in fact. It should be noted that for remaining homogeneous manifold, the space G mod H is always reductive. It's not so easy, but not so difficult to prove really, but it's very standard. We use the Riemannian structure to prove that there is some reductive complement. Okay. Now example, it's maybe the most important in this talk to consider some example. Okay, let's suppose that G is F times F, the direct product of two copies of simple compact Lie group F, and H is diagonally embedded F in this group. This is a definition. Then we can choose the following subspaces as reductive complement to Lie algebra. Lie algebra H is of this form. This consists of the pair U from F plus F, where F is Lie algebra of F capital, of course. And what we can consider as a reductive complement. For example, this one, this set, this linear space. This has form U0. Therefore, we consider only first non-zero component. And of course, we easily check that the dimension of this subspace is the same as F has. And easily check that this is a real reductive complement, because if we have some element of this type and some element of this type, then its bracket should be element of this type, of course. But you can take also this subspace as a reductive complement. Why not? It's possible. This is a standard methods to describe remaining symmetric space of type F plus F mod diagonal F. This is a compact symmetric space of class 2, yes. And another variance, another case, we can consider complement of this type. The first component is 0 and the second is arbitrary. It's also a reductive complement to this subalgebra in the Lie algebra G. Moreover, if we take any real number alpha and beta not simultaneously 0 and non-equal, then the subspace of type alpha u beta u, it's easy to check that it's linear subspace, is a reductive complement to this algebra H in G. Yes, really. Let's take some element from H, then this bracket, it's of this form, therefore in the same space when we take the first one. Okay. Therefore, this example shows that a reductive complement should not be unique, and therefore we can choose one of these complements for a given problem. I mean that if we consider different problem, then it's possible that different complement could be useful in different problems. It's strange, but it's really very important, very helpful idea. Okay. Now, a little about some standard way to find reductive complement. If G is semi-simple, then the Killing form B of the Lie algebra G is non-degenerate. Hence, one may define a reductive complement P as a B orthogonal complement to H and G. It's a very standard way to define some complement. It follows from the fact that all operators at A are automorphism of Lie algebra G, and they fixed subalgebra H for any A from H, and the Killing form is invariant under automorphism. Therefore, the orthogonal complement is also invariant under any automorphism, and in particular under any at A when A is from H. If J is compactly grouped, then the Lie algebra admit a G invariant inner product. Yes, compact does not mean semi-simple, but in any case, the Lie algebra G admit H invariant inner product. It should not be unique in general. Then one may define a reductive complement P as an orthogonal complement to H and G with respect to this add J invariant inner product, or bi-invariant inner product could be said. Okay, it's standard, two standard way to define complements. Now about tangent space. Reductive complement P, we'll fix some reductive complement P. It could be identified naturally, in natural way, with a tangent space mx to m at the point x. It's easy. We can take any vector of P and we get some vector field and so on and so on and so on. It's very easy. We can you can check it formally without any problem. And we have a linear bijection between P and tangent space mx. If we have two reductive complements, say P1 and P2, then the vectors U1 and U2 from this complement determine one and the same tangent vector in the tangent space mx, if only if U2 is a projection of U1 along H. This means that the difference U2 means U1 is in H. This observation allows to identify some geometrical values, inner products defined for different complements. Yes. Now, maybe I skip this because it's the same, almost the same. Okay, now a little more complicated structure. If we consider any H invariant inner space, inner product on P, then we can diagonalize this inner product and the fixed inner product simultaneously. It's very well-known result from linear algebra. If we have two inner products, then we can diagonalize it simultaneously, yes? Using also decomposition of suitable H invariant submodules into some orthogonal sum, we see that after this simultaneous diagonalization, we can represent of inner product this as in the following form. It is a multiple of a given metric inner product by some positive number in various directions. Directions means some submodules P1, P2, PL. This means that P is a direct sum of these submodules, and every of these submodule is at H invariant. And hence, if we have some decomposition in such sum, then we can define very easy family of inner products by this formula.
Can I ask you again? So
Yeah.
the original inner product, this with square parentheses, yes? With the angle parentheses. It's also a joint invariant, is it?
It's as usual, it's supposed to be at G invariant. Yes, this one is a restriction of some H invariant metrics on Lie algebra G, but it's not so important. You can take any at H invariant inner products, and you can consider one as some modification of second one.
Okay, and x1, x2 is some scalar multiple?
Yeah, positive scalar multiple.
Positive scalar multiples. And
yes, because it's Riemannian manifold.
Yeah, okay, of course, sure. And each this P1, P2, and so on, this is just also add H invariant subspaces.
Yes, irreducible, not necessarily reducible, but invariant. But if we consider all possible space of metric of such kind, then we can consider the sum decomposition of P into the sum of at H irreducible submodules, irreducible, and then on each submodules we can modify the standard, say standard inner product by multiplied by some scalar, positive scalar. This natural family of inner products.
Okay.
Yes. It's okay?
Yeah, thank you.
Note that in the case when all these submodules are pairwise non-isomorphic as at H modules, it's really very easy to check are they non-isomorphic or isomorphic. Then the decomposition of such kind is unique. It's very easy. I recall that the space of positive Euler characteristics are very special because many calculation are simplified in this case. This is one of the reasons why this is fact. Okay. Now example. Yes. If we have two equivalent H modules, P1 and P2, say, then there is some H equivariant linear bijection between them, say phi. It's linear bijection with which commute with every at A when A is from H. It's easy to see that this construction, P tilde, which contains the elements of this kind, AX, BY, yes, from P1 plus P2, where y is phi of x, it's H invariant modulus for every AB, for every real AB. Say we can take 1, 1, 1, 2, 1, 3, for example, if you want. Moreover, if we consider these two models, P1 tilde and P2 tilde of the above kind with some restrictions, here we have AX BY, CX DY, and AD minus CB is not zero. Yes, linear independence, yes, between vectors AB and CD. Then the sum, direct sum of these models is the same as the direct sum of original models P1 and P2. Therefore, we can consider the sum of two models P1 and P2 as the sum of these models. Therefore, we have another decomposition of the in this formula 2, because we can replace P1 and P2 to another P1 tilde P1 P2 tilde, for example, and get another inner products. It's quite possible. Yes. Therefore, if we have at least two equivalent submodules, we have more complicated set of inner products on our space. Okay. And another one methods to construct new inner products. Okay, almost the same assumption. We have Euclidean matrix on G, Lie algebra on G, and we consider some orthogonal reductive decomposition. P is orthogonal complement to H. Then we know that this restriction of this bilinear form, this inner product to P, determine a normal homogeneous Riemannian matrix. Its definition, one more. We take H invariant Euclidean metric only algebra. We have orthogonal complement to H with respect to this inner product, and we consider a restriction of this inner product to P. This restriction determines some inner product, of course, and some, consequently, some Riemannian matrix by the general scheme. Hence, we have some Riemannian matrix, and this matrix is called normal homogeneous because it produced by these methods as a projection of some bi-invariant matrix on Lie group G. In this case, we have some alternative description of the self-invariant matrix on the space G mod H. Indeed, for any H invariant inner product of this type, let's define the map from P to P by this formula. This is one inner product. This is another one, fixed inner product. It's easy to see that they connected by some operator P, which is the, of course, projection between P and P. And moreover, this is a symmetric operator with original inner product and positive definite because we deal with Riemannian matrix. Therefore, we can consider all this expression and say that this is a new matrix, new inner product, and let's consider the Riemannian manifold with this inner product. Why not? It's clear that this operator P is called metric operator or metric endomorphism, the metric endomorphism of corresponding Riemannian homogeneous space. Therefore, set of all G invariant Riemannian metric could be identified with the set of metric operators for a compact space, for any compact space. Sometimes it's very useful to consider this type of parameterization of all inner products on a given homogeneous space, compact homogeneous space. Now, a little about formulas for calculating curvature characteristics. It's very standard notation. I recall maybe this one. This is a formula of assumption for Riemannian curvature tensor. This is a notation for this one, for the length of the vector x, and so on and so on and so on. This is natural, the same natural notation. Sub-index G means the Lie bracket and the Lie algebra G. P and H are the P component and H component of these brackets. Okay, and this notation we preserve for the Lie bracket of vector field on the manifolds. We have projection between vector fields and element of Lie algebra. Okay, now we can consider differential of the canonical projection G to G bod HM. It is a monomorphism Lie algebra of right invariant vector fields, because Killing vector fields are right invariant. And it is isomorphism if G contains the full connected group of isometry. Now identify X with these right invariant vector fields with its value on the in the points A. Yes, we obtained this formula. I recall this formula. Now we define some operator, technical operator U from P times P to P by these formulas. Why this? I explain. Using identification of tangent space at the point X with reductive decomposition P, it's easy to check that this derivative nabla X Y, it could be calculated by this formula. This means that the first part is skew-symmetric part, yes, and this one is a symmetric part of this expression. It's very easy to remember. Symmetric and non-symmetric part, skew-symmetric part. Now, if we have this operator U, it's very standard, then we can write down explicitly formula for Riemannian tensor of this form, Rx, Y, Yx, could be calculated by this formula, very explicit. You see this. P components, P component, G component, and so on and so on. And we use also the operator U. It's very easy formula, in fact, because if we can compare with general methods of calculating of Riemannian curvature, it's very easy, in fact. And another formula, if we have sigma, a two-plane in the tangent vector space Riemannian manifold, and xy be two linear independent vectors in this sigma, then the sectional curvature k of sigma of this manifold in direction sigma is a number of, is a simple definition, is this number where this square area of the parallelogram, yes. Hence, we have more or less simple formula to calculate sectional curvature. We need this one and the previous one. Yes. Now, if we have some orthonormal basis for a chosen inner product, then xi, for example, then we can consider the following formula, following vector z. Is the sum of u of xi for all I, and it's easy to check that the inner product between z and any x is a trace of at x, this linear operator or joint operator of x, and trace of this operator is just this inner products for every x from P. Therefore, we easily check that vector z does not depend on the choice of the vector basis xi. Moreover, z is 0 if and only if Lie algebra G is unimodular, because this means that all this operator at x has 0 trace. It's just definition of unimodular Lie algebra. Not also that trace of at z is z multiplied by z with respect to this inner product. With this notation, with this vector z, we can consider a very useful formula to calculate Ricci form, Ricci of xx. Ricci curvature is average of sectional curvature of all section, two-dimensional section containing a given vector x, in some senses average. Yes, it's easy to prove really, but not so easy by technically. But we have final formula. It's quite short in this form, and this formula it's very useful to calculate Ricci curvature for any given inner product on a considered homogeneous space. It's quite easy. Here we use B, Killing form, Lie algebra G. On all others defined above. And the average of Ricci curvature by any direction is a scalar curvature. Yes, it also has very simple formula for computation. This one. Scalar curvature is very important, say, for theory of homogeneous Riemannian-Einstein manifolds. Very interesting, but maybe we discuss it a little later. But the most important is that this formula is very explicit, very explicit. It could be calculated not only by hand, but what is more important, by using of computer with some analytical system of computation, for example. It's very useful idea to use computer for this, really. Yes, and finally, for this lecture, for today's lecture, several examples. Let G be connected Lie group with Lie algebra G, small. We can identify this algebra with a tangent space GE where E is the unit of the group G, for left invariant Riemannian matrix is generated by some positive definite inner products. Yes. The matrix at the point X is induced by Q, these inner products, with using of differential of the left shift. Left shift, this operation, we simply multiply by element X from the left, hence left shift, and the differential of this operation give us the methods to spread this inner product to all Lie groups. It's very easy by definition, left invariance. Okay. And more concrete example. In the previous example, we can consider G is U2, a very simple compact Lie group, three-dimensional, with Lie algebra is U2 small. And this Lie algebra could be identified with usual R3, usual three-dimensional Euclidean spaces, supplied with the cross product of vectors as a Lie brackets. If we take, say, these three matrices from SU2, then its brackets could be, it's easy verified that we have these relations. And in the basis E1, E2, E3, the joint operator at X, where X is a linear combination of E1, E2, E3 with coefficient X1, X2, X3, then this adjoint operator has the following form, this one. We see that trace of this operator is 0, hence the Lie algebra is unimodular. And if we take another vector of this kind, then killing form between X and Y could be calculated by this formula. You see usual Euclidean inner product, yes, for this killing form on the Lie algebra. Let's consider the left invariant Riemannian metric on group SU2 that generate the inner product Q on SU2 with this, their terminal basis A1, E2, E3. We see that at X is Q symmetric, as we see earlier, as we saw earlier. This implies the metric Q is not only left invariant, but also right invariant. Skew symmetric means more isometry, not only invariant from the left, but also from the right. Hence, we have bi-invariant inner product. In particular, U, operator U, is identical to 0. Therefore, we can easily calculate the curvature, tensor, sectional curvature, Ricci curvature, and so on for this particular inner product. And now some variation. In the previous example, we can modify this bi-invariant Riemannian matrix. For this goal, we consider an arbitrary inner product of the Lie algebra. And up to inner automorphism of the Lie algebra SU2, we have the equality. This arbitrary inner product has this form up to automorphism. You see A1, X1, yes, Y1, and so on. This means that we multiply our bi-invariance Riemannian bivariant inner product by coefficients A1, A2, A3, and this direction of E1, E2, and E3. For some suitable positive numbers A1, A2, A3, where X and Y is arbitrary vectors. Such inner products generate all possible left invariant Riemannian metrics on this three-dimensional Lie group SU2. Hence, we also can use the above formula for curvature to find very important curvature characteristics of this matrix, for example. Now it's time to stop, I think, because the first part is considered for this day. Yes.
Okay.
Other questions, remarks, I don't know.
I have one question. From the very beginning, you told that any homogeneous manifold actually, so you defined it as a C-smooth manifold and so on, but then you mentioned that this has analytic structure. Is it comes because of the property of the Lie group, essentially?
It's a property of Lie group, nothing more.
Okay. Thank you.
Yeah. I'm ready to answer another question. I try to answer.
Actually, yes, you write C infinity smooth, right? But do you have example where they're not analytic but C infinity smooth?
No, of course
because
not.
You talk about homogeneous, right? So everything.
Not. It's analytic in general, but we should not use this assumption in advance because it's automatically. C smooth, it's C infinity smooth, it's more or less, how to say, geometric assumption, but analytical is, I don't know, maybe not so geometric. But in our case, in case of homogeneous Riemannian manifold, we have this a posteriori. There are too many formulas here, I understand. It's not so easy, but it's maybe first step to start to do something with these formulas. In any case, if you take some Riemannian, some part of Riemannian geometry in your investigation, it could be very useful to consider some homogeneous space at first. Yeah.
Yuri, how big part of your book cover this first talk? How many pages in the book?
Oh, just a moment. Just a moment. I have it. Not far. I think about 100 pages. Something look like this. Yes, about 100 pages. It's about homogeneous space. Not only this, there are some very deep results in the book. Of course, I have no time to discuss it. It's very basic notations and so on. Only this.
Okay.
Yeah.
But the reader can go look on this again before we start the second lecture. We have 2 weeks.
It would be very nice.
Would be advisable, yes, to revise, yes, some notions in the book, comparing with the slides.
Yes, I know that there are some misprints, typos, and so on. Sorry.
It's freshly baked, freshly made slides, so it's natural.
Okay.
Yeah, I had a question related to this set vector that was a trace of the U. I wonder if you have some sort of geometric interpretation of this set.
You mean what set you mean?
So you have this U tensor, which is the antisymmetric, which is symmetric part of the the Levi-Civita connection essentially. And
Yeah,
then
I
you have a
understand.
trace over the symmetric part. So I was just wondering if you have a geometric
This one.
Yes. So then you define the trace as a tool to represent, if you go to the next slide, I think.
Yes, this one.
Yes, this one, yes. I was just wondering if you have a geometric interpretation of what this set is.
Oh, Z. It is a vector of mean curvatures.
Yeah.
Vector of mean curvature. Because if you have non-unimodular Lie algebra or Lie group, then we can consider subalgebra with the property trace at X is 0. It's codimensional 1 subalgebra. And in the level of the Lie group, we have some, how to say, surface, hypersurface in the Lie group, in the reasonable Riemannian matrix. And this vector Z means mean curvature vectors. Mean curvature vector.
Yeah, okay, yes. Very nice. Thank you for that explanation. Yeah, well, I have one more question. So you stated your Levi-Civita connection using right invariant vector fields. Is this because you want something that is actually F related to something on the manifold? When you are, or that is projection related to the vector field on the manifold?
I don't understand the questions really.
So if you do right invariant, no, if you do right invariant vector field, it actually has, well, like if you project down at any point, you actually get to a vector field.
I think it depends only definition. As usually we use the definition of Lie algebra as Lie left invariant vector field on Lie groups. If we consider another definition, a right invariant vector field on Lie group, then we have this identification very easy without minus. It's the same, just the same. And in many textbook, the author use this identification, right invariant vector fields on Lie groups. It is definition for Lie algebra, but it's not so usual really. As usually used left invariant vector fields. That's the reason.
Yeah, I was just thinking that if you quotient on the right, you break left invariant vector fields, but you don't break right invariant vector fields. So that's why I was wondering if that was the reason.
I don't know what to say really.
Yeah, okay. So it's just, okay, so if you're a right invariant vector field, you do, if you want to consider the flow, you multiply with x t vector field on the left. And if you then quotient out by the right, this still works down on the manifold. Whereas if you do it for left invariant vector field, you do it on the other side. And now if you quotient, you have something that is not uniquely determined. That's why I was wondering if you're using.
Yeah, maybe you're right. Yeah.
Otherwise, I really enjoyed that you have so many concrete formulas. This is, I think will save me some time in computations going forward.
Yeah. In fact, there are many other formulas in our book. There are some original formulas, in fact, which you could not find in some other source, I think. Some advertising.
Yes, well, you have to do that. For everyone else, if you missed something during this very nice talk, I put a link in the slides where you can find the lecture notes for this talk and for future talk. I will try to post this again with the next announcement. Me and Irina will have to cooperate a bit on that.
Okay, but right now you send this link in for all the participants in the chat. So people can save this link, but after the talk, we can send again this link to all by email, so that the people can look on the slides and recording. Yeah, thank you.